Hi, welcome back. Where on earth were we? Oh yeah, so we talked about big picture, what is verification. We talked about all the fun games around what's a system, what's a spec. We've talked about automating this, and that if your system and your spec are formal objects, you have a hope of automating this, but don't get too excited because you're going to have to pick a trade-off. No misbugs, no false alarms, automatic. Side note, I did not say sound and complete. I did not say sound and complete for a reason. The reason is everyone wants to be sound but incomplete. So people define their soundness and completeness that way round for their tool. And so you can find tools that are sound but not complete for various different versions of this. And then someone goes, ah, yes, but we mean sound but not complete for bug finding. So yeah, I find sound and complete cause confusion. Always type 1, type 2 errors. Again, I've never seen people use them reliably. So that's why it's no misbugs, no false alarms, because you know what these are. Anyway, we got to this code. So here is our system. It's a really simple little program. It takes in an array and a target. It returns a pair. This is a sort of C. I guess it's actually a bit more Java-ish as a language, but it's just one I made up. It's got a counter for the number of things that you've found, number of times you found the target. It's got a record of where the last one is, and it's got a counter. And you've got a while loop, and while you're less than the array length, if that thing matches the target, then you say you found it once, and that might be the last one. And then you loop back around, you increment I, and you return at the end. Okay? Really simple program. There couldn't possibly be anything wrong with it. Well, to know if there's anything wrong with it, we need a statement of what's wrong. Right? So our spec is all array accesses must be inbounds. So that's an example of a sort of built-in spec. As soon as you've got finite length arrays, you're going to want a check that when you access an array, it's a valid location. The returned last is also in A. Okay, so that again is a sort of built-in, but it's almost a built-in for the calling code. So maybe actually that should be a spec in another part of the system. And then the last one's a bit functional. If you found anything, then A brackets last must be the target. Okay, so that marker is an instance of the thing you are looking for. So this is both a count and a find program all at once. And this is a sort of functional type property. So do people have feelings for whether these are true?
The second one is not.
Why?
Because if we will not find anything last, stays -1, so -1 is not okay.
Yeah. So what you're saying is, if we were to come in here and we go round this loop, but we never execute this bit, then found never gets changed, no, last never gets changed, and so we could return -1. Okay, so the informal argument is about a trace which doesn't execute this. Okay, is there a shorter argument for that one?
If A is of length 0, then you'll never go around the loop.
Yeah.
So you'll return -1.
So we've actually got two different arguments. And one of them is about non-execution of a bit of code, and one of them is about this particular concrete input. Interesting. Maybe we'll come back to that. What about some of the others? Other people haven't said anything. What do you reckon? Are they true? Are they false? Are they horribly undetermined? You've said stuff. Let's talk to someone else. I'll say more stuff in a bit. These are not hard trick questions. Hey.
For number 3, is that meant to apply at any point during the program or just when it turns?
Asking the smart questions. I like this. This is one of these awkward formalization issues. I want it to actually be true when it returns. But this is the kind of ambiguity you have to hammer out. Because quite often, if your spec is about an invariant, then you actually find it's like, okay, this data structure will always have this form. What about in the middle of manipulating it? That doesn't count. Okay, so hold on, where exactly is this an invariant? Yeah, it's just brilliant, absolutely brilliant, insightful point. Is it true if it's at the end? Okay, what makes you think so? What's your evidence?
Because at the end, found there's no way to go from found equals found plus 1 to the end without also going through last equals I.
Okay, I like that. I like that. So what you've got is an argument about flow of code. And you said, right, okay, so you can't, if for found to be non-zero, the only way that would happen is if you execute this line. If you execute that line, then necessarily you will execute that one. And because of this, you have the required property. That's pretty cool.
Just to get a side point to that, I think the third point is partially ambiguous with if found then, because you're implicitly casting an int to a bool.
Yep.
So if like different OSs handle that differently. So what do we mean in the spec by if found?
Yep. Again, really good point. This is why it's formalize and verify, because often you will be shaking these kind of issues out. Nobody's pointed out that I haven't said anything about whether these are bounded numbers and how long the array is and what happens if you overflow. But let's not talk about that for now. But that is the kind of drilling down into spec stuff you need. Go on.
Also, in whatever programming languages, this is your array isn't generic. Who says that what's in the array is the int that you expect it to be?
Fair point. I'm going to axiomatically tell you it's an array of ints. But again, good question. So the first one, are all the array accesses inbound? How many array accesses do we have? I think we've got one. Now, is that always within the bounds? You look like you're nodding. You're nodding?
Yeah.
And you reckon it is? Cool. You got any feeling for how you'd argue that?
So the only handle you have on it, the only reference, AI, is within the scope of the while loop, which assumes I to be less than the length of the array. Okay,
I like it. So can I reflect back to what you said? So what you said is, here, for this to be run, this condition must be true, right?
Yes.
The loop condition ensures that.
There's one other thing I should point out is you can't have I to be negative because it's initialized at 0. There's no code between that initialization and the while.
Okay, yeah. So we've got a mix here. We've got something, okay, well, this depends on this condition. The only place the I is changed is here, and we only ever increment it. So therefore it works, right? Exercise for over lunch. Take the informal reasoning that people write down. Try and turn it into a formal calculus. It's fascinating. Absolute minefield there. Yeah.
Formal way of this determinants of the answer.
Hmm?
I mean, we could say that at the third line, I equals to 0, we have a bound 0, 0. After that, we have an upper bound, so it's 0, a dot to a dot length. Like, basically, an abstract interpretation of this static analysis.
Guess where we're going?
Later on, when we do I plus 1, it becomes the bound increases to length plus 1. Again, it's rebounded when we loop back.
Give me about 10 minutes, maybe 5.
Maybe something considered I just found logically, for example, return from last. And but the last request back in the fact get found, then A the element of last is target. Right?
Yeah.
But you see last equal to I, and I equal to I plus 1. How can I say that? Sorry.
No, it's fine. It's the increment afterwards thing. It's a really good detail to pick up. I'll talk about it a little bit later. If you're still unsure, let's chat afterwards. Right, so my way of formalizing this is that I'm going to turn our spec into verification conditions. So these are points in the program with an expression. And what we want to do is we want to say, if we reach this point, the condition must be true. Okay? And I'm also going to explode this from code into a control flow graph, because I like pictures. There are a few other reasons as well. So this is going to be our running example. Yeah, I mean, maybe you want to take a photo. If you're the kind of person who likes taking photos of slides, so you can refer back to stuff, you should take a photo of this one. Okay, cool. Right, so we talked about there being 3 start base camps for our ascent up the pyramid. Let's actually talk about some of them. So let's talk about over approximate. We've got a bit of a family tree. So static analysis, I always like telling a little bit of history because, you know, what we're making cultural observations, right? Each of these schools is a culture as much as it is a particular formalism. So static analysis, I'm going to argue that static analysis is as old as programming languages are. And the reason I'm going to argue that is the original Fortran compiler. One of the concerns about whether these high-level programming languages would catch on was about efficiency. And so a lot of effort was put into the Fortran compiler to make sure that the code it generated was efficient. And a lot of the effort actually went into analyzing the code so you could be like, all right, these accesses are distinct, therefore we can speed things up. This case does not happen, right? And although they didn't describe it as static analysis at the time, kind of is. So yeah, I mean, maybe static analysis is the oldest of the schools. Anyway, fast forward to about the 1970s. people are publishing static analysis algorithms. And a pair of French mathematicians noticed that there is commonality between these. And that although people write their algorithms out differently, they said, look, essentially at the heart of this, you're doing the same analysis, but over slightly different objects. Clearly, this needs mathematics. And so this is the start of abstract interpretation. And the two communities do interact. There's things that go back and forth, but you will find that each community has its own names and its own words for the same ideas. And so if you go talk to the static analysis people and say, isn't this a reduced product domain? You may get a strange look. So yeah, okay, well, what's the view? So foundation, we want to reason about all possible executions of our program. Okay, well, what if we ran the program, but instead of having one state of the environment, we had a set of them. And then we could kind of run the whole program in parallel on all of the things, okay? And if we did it with all of the states, then we run it and we would know every possible state for each location. These are all the possible states. It's a nice idea, but it's never going to work because it's too big and too slow. So what if instead of running it with the set of all possible states, we ran it with a representation of the set of all possible states? This is the switch from it's a set to it's a representation of a set is kind of the classic opening move of abstract interpretation. So I'm now going to fill a slide with some maths, and apparently that's going to make the world better. But essentially, all we are doing is going, we'd like to talk about a set, it's too big, let's talk about a representation of a set instead. So, we got some variables, and we're just going to assume that our environment is a map from variable names to, I don't know, rationals. This is, of course, a very culture-dependent assumption, right? You go to some of the schools, you go to the testing, and you're like, well, state, it's just a map from variable names to values, and they're like, you've left out everything else, you know, you'll get laughed out of the room. You go to some of the formal people, and they're like, yeah, that seems legit. So, and we're going to think about instructions within the program as maps between environment to environment. Okay, so so our environment, maybe we've got two variables imaginatively called x and y. So one instance of our environment might be x goes to 1, y goes to 0. Okay. That's an environment. Okay, that's the kind of thing we're talking about. And so if your instruction is +1, you know, x. So our instruction is, you know, x plus 1. Well, I'll transform that to that. Simple stuff, total functions, there is no magic here. So we're going to need a representation. And our representation, got a set of things L, and we're going to order our representation. Oh, sorry. We've got a set of things, our representations, and each representation describes a set of these. Okay? And we've got this map, gamma, that takes my representation and goes, mathematically, what does this describe? And we've got an ordering on our representations in terms of the size of the sets of things they describe. Man, I know I threaten maths, but this is a lot. Okay, let's have an example. So maybe our representation, we're going to map variables to intervals. Okay? So an instance of L is x goes to 0, 1. Y goes to 0, 1 as well. Actually, no, let's change it. 1, 2. Okay? That's an object that is in L. Okay? And our concretization map, gamma, takes this thing and it gives me x goes to 0, y goes to 1, x goes to 0, y goes to 2, x goes to 1, y goes to 1, x goes to 1, y goes to 2. Okay? That's your set of environments. So what we're doing is we're using this thing to represent that set. We want to use the set, it's too big, it's too clunky, we're just going to use this instead. Okay? And so we've got our example of our interval up there.
So the L and the uppercase L, representing the right part or the left part representing the right part.
This is an object which is in L.
Object in L, yeah.
We have a map, I should have annotated it on the right, called gamma. And that takes something in L to a set of environments.
So this set of environments is the big L set.
So L are these maps to intervals. These are sets of environments.
So what is L? Uppercase L.
L, in this case, I didn't want to write it up, but it's the set of all possible ones of these. So it's every map from x and y to an interval. Yeah, I mean, it's so what were we calling this? The set of variables. So it's maps of the form x goes to something like that. X is all of the maps that go from x to pairs of intervals. Just L contains things that look like this.
When you concretize, you represent all the possible rationals in the environment. You do that in the environment goes from variables to rationals.
Yeah, you're right. Sorry, I was doing this with it, integers. Yeah. If we're doing this with rationals, I might just change my mind. Right? I might just cheat and do this, fix it this way. There you go, it's right now. But yeah, if we were doing it with rationals, this set would actually be infinitely big and contain a huge number of possible valuations. Point is, we have something we can usefully represent in computer memory that, although we never compute gamma directly, represents a big set that we don't want to deal with. That's the representation part. That's the bit I did in red in our introductory slide. That's the intuition, right? So then we want to be able to do stuff with it. So what we want is, for each instruction, we want to be able, an instruction will take an environment to an environment, right? So if we're working with sets of environments, we want an instruction to do x plus 1 everything in the set. Okay? And so what we want is a transform function which takes your instruction, your representation of the set, and produces a representation of the set after that instruction. That sounds really complicated. It's not actually that bad. It's basically, if you've got a bunch of intervals, and you've got an interval I 0 to 4, and you do I plus 1, well, you want an interval where I is in 1 to 5. That's it. And you're allowed to over-approximate it as well, because sometimes, if you multiply two intervals, what's the best interval that contains their product? It's going to contain some other things as well. But that's fine. It's a representation. And you also want to be able to merge these things. And this is just set union, okay? You essentially want to take two of these sets that you're representing and do a union of them. And again, this is a lot easier than you think. So if you're using intervals, and on one side, I is in 0, 4, and the other side, it's in 1, 5, then you can just work on the representations. You never need to compute gamma. And you can produce something that represents an over-approximation of their union. This is probably the most mathematically dense slide in the entire talk. And then you need a widen. Widen is a little bit controversial, but basically, the popular formalization of this is that it's like a merge, but it guarantees termination. Once you widen a bunch of times, you will eventually wind up with a fixed point. Finite number of widenings, you'll get a fixed point. If that seems mathematically slightly iffy, yeah, it is. Now, if you've, how many people know cleaning algebra? Sweet, a few people do. This is sequence, this is disjunct, this is cleanly star. Each time you want to be able to compute an over-approximation. You want to compute a representation that over-approximates what would happen if you did it for real. I'm seeing a lot of lost-looking faces, but it'll be all right.
Do you always want winding to be a function like this? Like, obviously the real objective is to have merge, but the merge isn't going to terminate. So you want some way of over-approximating the limit of the sequence, right? But
Yeah.
this isn't. There are ways to do that that aren't by over-approximating each individual step. You might
Yes.
have like a sort of history-dependent widening, which is
Yes.
like, okay, I'm clearly not going to. You get coarser as you go along to speed things up.
Yeah, yeah. This is one of the conventional presentations, and yeah, there are issues with widening. Right, so that's an awful lot of maths. Go for it.
Now, you making an analogy between this and clean algebra, say the transform function is like sequence.
Yeah.
But then the typing is not quite fitting in exactly.
Yeah, you're right, it's not. But what I'm trying to do is link up with the intuition of why you need these three operations. And in a moment, where I hope I can gather up everyone who got lost, I'll show you how we use this lot. Right, so we've got our program. Same program we had before. And what we're going to do is we're going to track an interval for found, an interval for last, and an interval for I. And we're going to run the program with intervals rather than values, which probably sounds a lot more sensible than all of that. But all of that is why we can do it. Okay? So let's do it. Right, after the first, to start with, all of our intervals are top. Actually, no, we're not. We're going to start out with them being, there is no value. This variable has not been declared. Okay? So after the first one, we're going to store a set of intervals for every program location. So after the first one, we've got an interval for found, which is 0, 0. So you can guess what we're going to do next, right? We've got an interval for last, which is -1, -1, I, which is 0, 0, right? I've just said these are constants, and I've said it in a fancy way. Let's do some more. Right, we get to a branch statement. Now, because we're trying to over-approximate what the program does, we're going to need to try out both branches, okay? So I'm going to need you to keep track mentally of places that we haven't been yet, okay? So we're going to go down one branch, but we'll come back and do the other one, right? So, first off, if we go down this branch, well, these are verification conditions. They don't change the program, right? So we're still going to have the same environment as before. Okay, now we go back and we're like, hold on, there was a path we haven't explored. And so we're going to do it. We're going to go down this way. I is less than A length. Well, we could use that, if we knew anything about A dot length, we could use that to reduce the interval on I. Unfortunately, we don't. So, yeah, look at that. And so, at this point, we're still going to have the same interval. Verification condition doesn't change anything. Here, we've got to a branch. Again, we're going to have to do both sides. So here, found. Okay, so found after executing this, well, found was 0. It can now be 1. If we've taken that branch, it will be 1. Okay. Now we've got a bit more of a problem, right? Because we're going to come back and we're going to merge. Okay. Our control flow will come back together. That's where we need our merge operator. Because on one branch we've got that found could be 0, And on the other branch, we got found that could be 1. Okay? So, we need to bring those two together. And so, we wind up doing this merge operation. And we wind up with, okay, well, found could be 0 or 1. Last could be -1 or 0. But I is definitely 0, because it's 0 on both branches. Okay? And now we've got here, okay, well that goes back, so we're then going to need to do the merge into this one. Okay? And previously it was like, okay, well, 0, 0, it was all constants. But now we've taken what we've got and merged it back in. So where the control flow branches merge, you do a merge. Where you've got instructions, you do a transform. We are just running the program with intervals, not values. And of course, because we've changed that, we need to keep going. So we ripple all the way down and make our changes. And now we've got, well, it could be 1 or 2. And we keep on going back round. Now, the astute amongst you will have noticed that this process could go on for some while, right? And we're slowly increasing the values.
Simple question. So I found it that in the square bracket, at least not interval on the right. For example, 0, 1 or 1, 2. They are just least, not interval.
No, these are intervals. At the moment, they only contain values that are actually achievable. But you could use a list, right? There is no reason that you can't build an abstract domain that uses a list of values. Your problem may be size. So we can keep on doing this, but this is then when we need the widen. Now, yeah, we go around again. And each time we're widening the intervals. So what we want is that the widen goes, well, there is clear progression here. So can we jump ahead of that? Can we jump to a termination point? And I've put X in because depending on how you implement your widen, you will wind up with different values going in the X. Okay? So a simple implementation of widen is you just look, okay, which interval bounds are changing? Okay, make that infinite. Make that the top value. That will terminate, and it will terminate quickly. Alternatively, you might do widening by incrementally upping the bounds. So you go, okay, let's try, what happens if we put 2 in there? What happens if we put 4 in? 8, 16. You can do an exponential back off. If you're really, really clever, you can pull out constants that turn up elsewhere in the program and try and use those. But this is where the magic is kind of point. So once we've done this to a fixed point, because we know that the transform's over approximate, and because we know that the merge is over approximate and the widen is over approximate, then when we got to a fixed point, that's it. You have an over approximate description of what the state of the program can be at any given point. Cool. So from that, we can handle some of our verification conditions. Okay? This one. 0 less than I less than a length. Well, if we can pick up that the X is actually array length, if our widen is capable of doing that, then yeah, we can prove that one. Go us. Unfortunately, this one we're not sure about, right? Because our interval on last has -1 in it. And you could say, okay, well, that's clearly, it's going to break it. The problem is that because each of our steps are over approximate, we don't know whether that -1 is real or not. It might have just turned up through an unfortunate over approximation. So we have to go, actually, that one's unknown. This is where the unknownness starts to creep in the verification. And the last one, unfortunately, we're not tracking a lot, the values of A. So we can't really answer that one. Annoying. But hey, good news. We've proved a third of our spec. I'm afraid I'm going to have to skip the exercises because I've talked way too much. Pros and cons. Pros. Assuming independence is an over-approximation. This is a phrase I wish somebody had said to me years ago, because an awful lot of the power of abstract interpretation comes from this, from over-approximation, from assuming independence. So one sleight of hand that I did that you didn't even notice, maybe, is that I'm tracking intervals separately for x and y. That's assuming they're independent. And that makes it really scalable because I only now need one interval per variable. I don't ever need to consider their interplay. So there's a lot of cases where you can be like, okay, this is a complex linked system. Fuck it, let's just treat these as independent parts. And suddenly it scales loads better. But it's over approximate. Also, you can discard information. If you get stuck, you can just be like, you know what, this could be anything.
If you discard the independence and you start considering the interaction between variables, does that get rid of the over-approximation or less?
It increases the over-approximation.
Increases or decreases?
Increases. It means that if you... if you've got x and 0 and 1, and you work out this, you realise that that has to be in 0, 140. Because you can make that as big as a half, and if you make it any bigger, the other side will be biggest. Now, if you over-approximate this by assuming they're two independent variables, if you treat those two things like they're independent, suddenly you get a much larger interval. Assuming independence is an over-approximation. That's the simplest example I know of. If anybody knows a better one, please do tell me.
The first one, isn't it like a pro of the interval abstract domain and not just interpretation? Because there are other abstract domains where the independence is not there.
Oh yeah, I mean, it's up to you how much independence you introduce, right? But a general factor of the over-approximate techniques is that you have a trade-off. You don't have to treat coupled things as coupled. You have the option of being like, yeah, I'm just going to treat these as if they weren't. And the more you do that, the more you over-approximate. But it's a line in which you can do a trade-off.
Is there any way that you can actually reintroduce the more knowledge you have about variables and their interrelationship after the results of the interval analysis? So you could say, well, it's an over-approximation, I got these results, but I know some of these will or won't happen. So I can reduce that step even further.
There are ways of doing it, but you run into these kind of problems. The yes, but why? Or the kind of... It's very easy to get... to write an abstract interpreter. It runs very quickly, gives you over-approximate results, but then comes back going, well, it could be anything. And yeah, if you know other things, you can introduce those. But if you know them, you could also just make an abstract domain of things you know and propagate that through. So, yeah, trade-offs. I'm running out of time, but there's a lot of things I'd like to get through. So let's try and do that. But could everybody just stand up for a minute? Have a bit of a shake. Have a stretch. Yeah, you just got the right idea. Okay. Cool. Okay, sit back down. No, seriously, like, you're not going to be able to pay... Like, I'm going to try and do like, you know, some non-trivial stuff at speed. You need a bit of, like, a bit of motion. And I was going to get people to just move around the room and talk to each other, but we're running out of time, so... Right, under-approximate. Our next school. Sure. Because it's simple. It's simple, and it's got a really nice intuition of running the program with an interval. But the nice thing about abstract interpretation is you can pick whatever domain you want.
But once you pick the domain, if you add extra stuff, you have to change the domain. I guess.
Yep. And so you'll find, if you like the category theory, you'll find that yesterday, the composition of domains forms beautiful categorical things. And so you can be like, I'm going to have this domain and this one, and they're going to exchange information and compact, and you can do all this lovely calculus of different abstractions.
So that arrow here is mapping or means assigning one to X value.
So this is an assignment, and this is a mapping on environments that it represents.
In the big parentheses.
Yeah. So good point. This is its current value is assigned. So this is X, in this environment, X is 1. Yeah. And then we do the transformation given by this, and then X is 2.
Yeah, so that's similar to the middle one as well.
Yeah, yeah.
So that star represented here in your application.
Yes.
Okay.
Yeah. Right, so let's do under-approximate. See if we can do all of these. The under-approximate family tree is a bit more complicated. So you've got the testing community, and symbolic execution splits off testing. The model checking community starts out with people interested in essentially automata and temporal logic. And you look at the semantics of temporal logic, and it says, okay, the objects you're reasoning about, the models for your temporal logic are automata-like things. So if you have an automata-like thing, and you have a temporal logic formulae, you can verify that that system meets the specification by checking whether your automata is a model of your temporal logic. This is why it's called model checking. This is how it started, and this is then why even down here, everyone goes, well, of course, a program's just a transition system. What else would it be? There have been several different sort of eras of model checking. The oldest are the explicit state systems. And they are generally actually exploring the possible states of a system. So spin is the big success out of that. In 1990, somebody hit on this idea. Hold on. Rather than a set, like actually having all of the states, we could have a formula which represents a set of states. They didn't do it like this. They independently reinvented the idea of a representation to describe a set that's too big for us to work with. This led to all the SMV, and this is all the BDD algorithms. About 1990, someone said, okay, that's great, but these things are kind of big and unwieldy. Could we solve a simpler problem? Rather than trying to work about the behavior of the whole system, why don't we just work out the behavior up to k iterations? And it turns out that because there was new solver technology available in the form of SAT solvers, the k steps problem could be reduced to SAT and suddenly runs tons faster than the BDD thing. This is how Armin Bier got his PhD and starts an absolute revolution. A section of that world then starts to do software. Up until this point, these people are mainly caring about hardware and process calculus. And if you go to model checking events, there is still very much that view. There will still be a lot of people talking about that kind of thing. But a section of them are like, hey, we could do software. It sounded like a crazy idea. But actually, yeah, we can adapt this. Except, of course, that the step they wind up doing to convert software into a symbolic transition system is symbolic execution. So that gets reinvented as well. Eventually, the name gets picked up too. But the point is that these people view symbolic execution as like testing, but covers more values. These people view symbolic execution as, oh, just a way that you can build a transition system. Same technology, different purposes, different cultural role, and therefore they use it differently and think of doing different things with it. And then again, a lot of this is driven by the availability of reasoning tools. So the step from explicit state to symbolic state, this is because people have written BDD libraries, and you can use them. From symbolic state to BMC, this is because people have written SAT solvers. From BDD to some of the interpolating systems, IC3, PDR, this kind of thing, is because people have written SAT solvers or SMT solvers which are capable of doing logical interpolation. There is a very tight link between each time the automated theorem proving community builds something cool and new, you get a new class of model checking algorithms. If you're speculating about the future, you might want to think about that.
I've got a couple of questions about this tree.
Yeah.
The first is that you put bounded induction with bounded model checking.
Mm-hmm.
That focusing on the bounded or focusing on some other latent characteristics such as, I mean, you mentioned that BMC is kind of found a success due to advances in SAT solving. Is that true of bounded induction as well? Or is it
So specifically K-induction, I'm putting there for cultural reasons, because you read the original BMC papers and they say like, okay, well, we're going to explore up to a certain depth.
Yeah.
And then at the end of the paper, they're like, oh, obviously systems have a diameter. Again, their systems, they're thinking of state machines or circuits. And they're like, look, there is a finite length of trace before you start repeating your state. So if you've got a buffer in your hardware system, it's only a certain length. And so they make this argument about diameter, which is at a certain point, your K is large enough. The K-induction people are trying to pick up on that and go, hey, can we actually make that observation more formal? Can we turn that into an algorithm? And so, although various other people think of bounded induction, there is a stream of it here which is directly connected to the early BMC papers, because it turns out that once you've implemented a bounded model checker, implementing K-induction is easy. So yeah, that's why I'd put it there. But this, as I say, is somewhat cultural, and people reinvent stuff.
Yeah. So my second question is similarly on the cultural side, because I think of CEDAR as more coming from abstract interpretation.
I strongly disagree. You look at, so CGAR uses over approximation, so it's one of the points where the pyramid doesn't quite work. But if you look at who's developing it and why, the early CGAR papers are attempting to take software and reduce it to something that will fit in a symbolic state model checker. So all of them are, hey, we've got SMV, or new SMV, or XSMV, and we'd like to use that for software. If we came up with some predicates, there's this little symbolic execution trick we can do that will glue it and turn the whole thing into an automata. Great, we know what to do with automatas. You feed it in SMV. And this is them rediscovering predicate abstraction that the abstract interpretation people have been talking about for years, but this is an independent discovery motivated by different reasons. So yeah, if you were classifying by the maths of it, yeah, of course it doesn't belong there. I'm classifying by the culture. So yeah, all of this is just like a pyramid, a way of looking at verification. It's not the only one. Right, so foundations. If we've got one test case, we can run it and get one execution. Cool. That was dramatic. So can we generalize it out to similar traces? Well, if we use logic, and again, this is another set of people rediscovering the whole, like, we can describe a big set we want to talk about with the representation. In this case, the representation is logic. We can describe the set of things that take the same path. So, again, let's do some maths. We've got a set of variables. No, that one's attached. Thanks. I'd have to wipe this. Yeah, I need that one later then. If we make it, that will be making a return. So, but thank you. Right, so. we have our set of variables, x, and we're declaring some of them as input variables, okay? So maybe we've got x is a set x, y and I, because I'm really imaginative, and I is just the set that contains I. Then we're going to want a set of expressions that can be built up from I, okay? Well, 0, 1, I plus I, 3I plus 1. This is an awfully big set, right? And we might also want the predicates that we can make up over I. So we might want things like true, false, I is less than I plus 1, 3I equals 2I plus 7. Again, it's a really potentially big set, okay? And so what we're going to do is we're going to represent the set of states of our program with an environment map, which takes x to expressions and a set of predicates. And our operations on this, if we assign, then what we do is we get the expression for one op, the expression for the other one, build the new operation, and store it. Okay? And if we branch, we evaluate the expressions to get the symbols for them, and then add it into the program condition, the PC. And we can also do a satisfiability check on the program counter. And if it's unsat, we can throw the whole branch away. Again, this may seem complex, but basically we are running the program with symbols and expressions, not concrete values. So this echoes our running it with intervals thing. But there are a few subtle differences. Right, so let's actually give it a go. So, we're at the start now. We need a path condition, and at the moment that's empty. Okay? And we're going to need our environment map. Okay? And at the moment we don't have any variables, so actually, no, we've got input variables, right? Because we had A and target. Okay? So A and target. And because these two are our inputs, we're going to give them a symbolic value. Okay? And the symbolic value for variable A. Does anyone mind if I just call it A? Why not? I mean, if you don't like that, we could call it A at the start. Target. I'm not going to change them, so it doesn't really matter. A and target. So, let's run our program using this as the state. So we need to do 3 steps. We need to do found is 0. Okay, so we've got a new variable. We'll call it found We're going to take that 0 and we're going to replace any variables we find in it with their current value. And we're going to wind up with the expression 0. And then we're going to do exactly the same thing for the others, because this is done. Last is -1, and I is okay. So that's the current state of our interpreter when we've got to this point. Now we've got a branch, and we need to pick one way to go. Because unlike our over approximation, we don't have a nice merge where we can bring things together. Trick, there is actually a way of doing it, but at the moment on our slide we didn't tell you how to merge things. So we're going to just pick one branch. So I think I'm going to pick the branch that goes out. And again, we're going to have to keep track that we've got another branch that we haven't done. So I'm going to pick the branch that goes out. When we get to our verification condition, and we can check this, right? We can do a SAT check with all of these things and the condition 0, last, a, length. Is it possible that that's not true given this?
Quick question. What that P
This is PC.
PC.
Sorry, I have awful handwriting. This is our path condition. This is part of the state that we're maintaining. Okay. So is this satisfying?
Sorry, I think I might have missed it, but what is the input variable and what is the
So our input variables are a subset of our variables. They're the ones that we're going to treat symbolically.
So all of these are.
No, just these ones. These are the two input ones. These are the rest of the variables.
So our predicates would be only over our input variables.
Sorry, say again?
The set of predicates
Yep.
only over the input variables.
Yep. So, in which case, we need to substitute, right? So, last, we take the expression that's there, it's -1. So, -1 is 0 less than -1. No, it's really wrong. Okay, false. So, negate it, whole thing's true. We have a genuine character. What's more, we have a concrete path through the program to that location that says, here, if your state is like this, verification 2, condition 2 will fail. We've found a counterexample. Sweet. That part of our spec is definitely wrong. Or, more appropriately, our system does not match the spec at that point. Right. Let's get back to another path. Because we can go on, but yeah, we can go on.
Sorry, one question.
Sure.
In that part, actually, that is symbolic for the negative, for the false.
Yeah, because we want to know when these things fail.
False. That doesn't that one part.
Yeah, so if it was false, the whole thing, and it was true, the model is satisfied, and therefore you have a counterexample. At this point, we can do the other one as well. So found is equal to 0 implies a last equal to target That's the thing we want to prove. Well, actually, we want to show that that's not true. So try and find counterexamples. Not that. Should be just in terms of input variables. Let's do the substitution. Found, look up its value, it's 0. Last, it's -1. Oh, okay. Yeah, this is, well, that's false, right? And false can imply anything. So, yeah, the thing will be unsat, and so at the moment, we haven't found a counterexample to this yet. Now, that doesn't mean there isn't one. It just means this path hasn't found one. But other paths may reach here. So we can't just say this is fine yet. So then we have to go back and consider our other path. Okay? And, well, it gets in here. We need to check this. And again, if you want, we can write it out and substitute in and do the sat check. But actually, this one, yeah, this condition holds on that path. Okay? And so then when we get to here, well, do we take it or do we not? Okay, let's not. So if we're taking a branch, we need to add to the path condition. So we need to take this A, I, equal to target. We get to add that, or actually, because we're not taking the condition, not that. Now that gets permanently added to our path condition. Oh, we've got to substitute it. I is currently 0. Okay. So now, all of the sat checks that we do in the future will always assume that this is not true. Because every path, we didn't take that branch, so every possible path that extends on from this, we will need to keep that in mind. Okay? And so we get to the bottom, I equals I plus 1. Okay, now we can update this. So we look up what I is, it's 0, we add 1 to it, we get 1. And we update on that. And then we get back round. And we keep on doing this. Whenever we assign, we update on that. Whenever we branch, we add a path condition. And we also mark that we need to consider the other path. You can start to see where this can be born. Because each time we go around the loop, we add more paths we need to consider. This is the path explosion problem. There are some things you can do to fix this. So with a little bit of thought, you can probably actually merge 2 of these states. And that helps, but we still don't know how many times we're going to go around this. And so even if we're merging when we get back here, or merging when we exit, we're still going to wind up with an ever-growing number of paths. And worse, each time we go through a choice, we add to the path condition. And yeah, if we merge, we can throw these away, but they wind up getting stuck in the environment. And so we build an ever bigger expression. So the failure mode on abstract interpretation is that we just wind up going, it's top, we've thrown away all of our things. It could be anything. Is our spec right? Who knows? You know, back to the like, your code might be wrong. Your failure mode on symbolic execution is that you keep on burning more memory, more time, and all of these, you're like, well, we haven't found a counterexample to it yet. So again, so then we're going to have to wind up marking these two as unknown. Because we haven't found a counterexample yet, but we haven't closed all possible branches. So maybe there's another route that we just haven't looked at that will trip us up. Yeah, if you want to go at the exercises, mail me, I'll send you the slides. Pros and cons, the amazing thing about a lot of under-approximate techniques is that you get genuine, concrete counterexamples out. And if you're thinking about industry, if you're thinking about how you demonstrate the value in what you do, being able to go to people and go, yeah, can you run the code with this input? Just let me know how that works out. Is such a powerful thing. It helps with industry. It also helps often with your understanding. It makes it a lot easier to find bugs in this, because bugs in an abstract interpreter, often you wind up being like, it said top, and all the domains are huge. I don't think they should be that big, but I can't really articulate why. With this, you're like, no, that counterexample is definitely wrong. Anytime. You can stop doing this at any point you want. You will have some evidence. With a lot of the over-approximate techniques, you've got to do the whole thing. With this, you run it just a bit, you got a little bit of evidence. You run it longer, you got more. Downside, combinatorial explosions. Modularity, for those working on incorrectness logic, fix this, please. We want modular under approximate things, but that's hard. Also, little appreciated, you need a complete program. It's very difficult to under approximate a missing bit of code. What does it do? It can do anything. We can't just put anything in. So, right. Let's try and do it. Everybody stand up again. Come on. We need a little bit more energy. Have a shake, have a stretch. We're going to finish this. It's going to be great. Right. Sit down when you want. Right. Sure.
Do you think the cost on the backbone is caused by the path exploration? The path exploration under approximation caused all the counts, for example, so many, because we have to trace on the trace all the paths. For over approximation, we try to over generalize, for example, set of branch into one more hierarchy level. Right?
Yeah. Essentially, yes. So, like, part of your problems are coming from this combinatorial explosion of paths. And in the over-approximate case, you can just merge them. And you just merge them and be like, it's an over-approximation, but it's fine. Let's just slap all of them together. And that comes at very low cost. Whereas with the under-approximate case, when you slap all the paths together, you still build up cost. And you may have got it out of the number of paths you're looking at, but you've pushed that complexity into the solver. And it may handle it better, but you're ultimately not getting around. You're moving where your combinatorial explosion is. You're not actually fixing it.
And in each branch, you will observe every individual variable.
Yep.
Yeah, so that's possible.
Yep.
I have two questions. First one, that you mentioned the two pros. One was that you could have stopped at any time on your counterexamples. aren't this better approach if you just use testing instead of formal verification? Because the whole point of formal verification is this stated IAM to have formal verification.
Yes, but this is why I said evidence at the start. Right, is that yes, you can do this with testing. You may find that the evidence you get covers more possible cases. There are some classes of program, particularly things with sort of very wide variable ranges, where if you just do testing, you're just doing drops in the ocean. If you're doing some of these under approximate techniques, you're sort of taking a river's worth out at a time. So if you're thinking about the rate at which you're covering the behavior of the program, you may find that you're doing more using these more formal techniques. But it's the same trade-off applies, right? When you're talking about testing, how much testing do you do? How do you know when enough is enough? It's exactly the same trade-off.
My second point was like this can also be the pros for abstract interpretation, because if you have a big abstract domain, you can just divide it into like 1,000 parts and do one of them one by one, then you have an anytime solution. Plus, this can you can use gradients to get counterexamples in abstract domains.
Yeah, you can, but these are not these are not necessarily the usual and obvious things to do, right? Is that if you build a symbolic execution system and it doesn't produce counterexamples, culturally everyone will think that's very weird. If you produce an abstract interpreter that doesn't give counterexamples, no one will give it a second glance. So yeah, if you start bringing in some of the under approximate techniques to your over approximate one, then you'll get some of the benefits. Right, human assisted. How many people have done Hall logic? Okay, well, my apologies for everyone else because we're about to speed run it. Right, so history of this. There is an entire school of verification which thinks about functional things. They use types rather than annotations. Some of them even think they're a different thing. The interesting one there is ACL2. ACL2 doesn't get anywhere near enough press. It's an interesting, it's kind of the platypus of verification systems. Like, it's kind of this little, you know, it's the only evolutionary branch that's just gone off and done crazy things. But yeah, there are then, within sort of deductive verification, there are actually kind of two schools. There's the Dijkstra's view of programs transform predicates, predicate transformer view. And then there's the Floyd and Hall logic school of like, no, we have logics, and a logic connects predicates with program. And people act like they're different and get really evangelical about it. And then you find that every interpretation kind of blurs the line. And you find that people who are like, no, we are definitely doing Hall logic. And you open their code up and you're like, why is there a weakest pre-transformer in here? And they're like, well, how else would you do it? So I put them as kind of parallel because often they're two different views of similar things. And both sides will get upset when I say that. Because the predicate transformer people are like, no, we have things that they clearly can't talk about. And the Hall logic people are like, there's method is ad hoc, we're a proper logic. Normally they're getting at the same thing. If you try and do anything large in Hall logic, you very rapidly realize that there's an awful lot of the description of the state of the system you are passing around is actually just saying about things that haven't changed. You change one variable, but you kind of don't want to have to talk about all the rest of the data structures that you haven't done anything to. But formally, you have to. So wouldn't it be nice if you could kind of separate your program up and have things that have changed and I'm talking about, and I want a proof that is local to the things I have changed. And then the rest of the system that I haven't changed, and it's just as proven as it was before. That'd be nice. This is the intuition behind separation logic. Incorrectness logic then is, I'm going to be mean. Incorrectness logic is what happens if you've got people from this lineage who suddenly discover under approximate analysis and go, oh, wow, that sounds really useful. We should make a logic for it. Because, you know, that's what you do. Trolling. Right, so foundational idea behind Hoare logic is that you describe the set of possible states at a program location with a predicate. This is the third reinvention of this idea, because the abstract interpretation folk were like, oh, we want to talk about a set. Let's talk about a representation of a set. They didn't necessarily use logic, but you can. The moral checking people were like, hey, explicitly representing all of these sets is damn complicated. Why don't we use a BDD to talk about like a set of them? And then people are like, BDDs are great, but they're too slow. Why don't we use a formula to talk about a set of them? And then the deductive verification people are like, oh, right, so you're finally coming around to our point of view. But yeah, so we're going to describe a set of possible states at a program location with a predicate. And we're going to use logic to link these together. And here's the spicy part. Here's the good bit. We're going to use proof by induction for loops. Because this is the 1970s, and we've got mathematicians looking at this. So let's put some symbols on this. So the kind of key idea that will turn up throughout all of the literature on this, unless, of course, you read the predicate transformer literature, where they use the same, a different notation for the same idea, is that we've got this Hoare triple, which is the state before the program and the state afterwards. And informally, if the state before meets the precondition, then after the program has finished, interesting question about what happens if it doesn't terminate, then the state will meet post-condition. And with a little bit of thought, you can probably come up with some proof rules. Like, if you've got one Hoare triple and another Hoare triple, you could have the Hoare triple for one program followed by another. If you've got one Hoare triple and another Hoare triple, you could probably come up with the Hoare triple for if one condition, the first one, if the other one, right? You're smart people, you come up with it. That's the one that is doing anything magical, right? And saying, well, if the invariant is true and some condition is true, and you know that the body implies the invariant, then you can build a while loop. This is your proof by induction rule. Right, I'm just going to, if you haven't seen this before, I'm sorry about the speed I'm going to have to do it at, but essentially we're taking our program and we're breaking it into 3 sections. We've got the before bit, and you've got to prove your invariant holds beforehand. You've got the after bit, where you get to assume the invariant holds. And you've got the middle bit. And if you assume that it's true at the start, then you've got to prove it's true at the end. So this is the base case of your induction, the inductive step, and the consequence of what you use your inductive formula for. Perfect question, perfect timing. What is P? Well, that's the big question. That's where the human assistance has to come in. someone's got to come up with what the predicate P is. And if you supply that, the rest of it's automatic. But somebody has to come up with this, or alternatively, somebody has to be tool supported to come up with this. But that comes externally to the algorithm. That's where your work goes. So I could just use verification condition 3. And if you work it through, you'll find that that is indeed inductive. And it lets you prove that one, but the other two, not. And the awkward thing is, like, that you don't know that this is wrong. You just know that it's not provable with that inductive condition. That's not the same as saying that it's false. So again, this is another area where that I don't know creeps in. And it turns out that if you use a slightly stronger invariant, then actually you can prove this one as well. You still can't prove this one. And from an operational point of view, this is a pain, because if you're just doing pure deductive reasoning, then if you've got a condition that you can't prove, do you think that it's false and regard it as a verification failure? Or is it that you just haven't come up with a smart enough inductive condition? And on its own, this technique will not give you that answer. So it's quite common for people who are working with this sort of thing. This is where the psychology comes into it. People are like, oh no, I'm convinced my code's right. If only I could find the inductive invariant that proves it. And they're trying and they're trying and they're trying. Days later, they're like, oh shit. And because your bias is towards believing that your code's right, you can burn a lot of time doing this. My big start on doing verification was doing counterexamples for this kind of thing, just to save people time. And go, I'm not saying your code's wrong, but consider this input. And yeah, we literally got it funded by doing a calculation about the amount of time people would spend thinking about these kind of things and how much we thought we could reduce it by, and multiply by the salary of an engineer. And they funded it. So, yeah. Pros and cons. Certainty. This is really, no, we verified the algorithm. Scalable. It turns out actually that once you've got the inductive invariance, you're just proving little straight line bits of code. It's actually quite cheap. You can, like, I mean, even 10 years ago, you could do like a 250,000 line project in a couple of hours. We've got a parallelized system. I think we got it down to you could do it over your lunch break, reprove the entire system. It's also nicely incremental. You can prove just parts of your system. You asked me a question. I said I'd get back to it. What was the question?
The question was, you said that, so annotations, so blur the line between hints and specs.
Exactly, right. Maintenance. So, you need your inductive invariant to prove this. Is the inductive invariant really part of the spec? Well, it includes fragments of the spec, sort of, but it's its own thing. Now, if you change the spec, do you change the inductive invariance? Maybe, some of them. How do you work out which ones you have to change? Try and reprove it, see where it fails. Is where it fails where you need to change the invariant? Not necessarily, it might actually have been earlier.
Sorry,
Sure.
P is here, in this context, P equal to VC.
3 and 0, yeah, less than that.
All the P here
Yep. Perfect. So the maintenance of this kind of software can become a complete nightmare, because when you want to change part of the code or change the spec, you've got fragments of the spec turning up in various different annotations, some of which are genuine conditions you want to check. Some of them are just, that was proved elsewhere and I need to move it around my program. That's the answer to your question. Right, bringing it all together. I started 10 minutes late. Am I allowed just a little bit of lunchtime?
Yeah, I mean,
Oh.
what the energy of the room is like, but yeah, it's like,
Okay, okay, let's do it. Right, bringing it all together. So, process considerations. You pick two of them. The thing you are saying to your project manager, the people who are giving you, if we're back in this world, what they're giving you £1 million a year to do is provide enough of the third one. And they expect you to make a reasonable effort. £1 million a year is a reasonable effort. How much is enough? These are not things that are directly answerable formally. These are cultural things you have to find, and these are some of the stuff that you might want to ask. What happens if it doesn't meet the spec? With some of these common attacks, it would be really, really bad for your company if there was an obvious common popular attack that could be done against this. Not only because of the cost of fixing it, but also because of the CrowdStrike value, the cost of reputation and the number of people who are not going to buy this because it's got obvious flaws. What happens if it doesn't meet some of the performance goals? More ambiguous. May only hit some of your customers. They may be large enough customers that with large enough wallets that you can go, well, just buy 4 more units. So how much effort do you spend on those? Ask them who uses the evidence. Is this, is somebody going to get called up in front of a parliamentary select committee, like has just happened, or worse, a legal inquiry, like Horizon, for the post office scandal? If so, you want to find out who in your organization that's going to be, and you ask them to fund your work. And you tell them how you are going to make sure that in 10 years' time, they are not there with a panel of QCs, or KCs these days, being like, did you show due diligence on your system? Can the system spec be changed? Can the tools be changed? Maybe you want to use an over-approximate solution. Maybe the abstract interpreter doesn't quite have the right domain you've got. Can you pay for it to be changed? Can you change it yourselves? Are partial results useful? Can you go back to them and go, well, you know what? Data checking. We've got a deductive verification proof that all of your decoding certificates will not crash, will be correct as long as they follow the standards. This is why I say evidence, it's always a caveat. That's not verifying the whole system, but it is ruling out one category of things that can go wrong. Is that useful to them? So yeah, process things to think about. Limits of verification. I want to get this written down more formally at some point, but there's this weird ass observation, right, that all of this is fine if the spec is right. And obviously you're going to do some validation things, but just as a quick rule of thumb, you want that the spec is simpler than the system you are verifying. I'm not going to name it, but there's at least one verification system I know of C, where they're like, here's like a 3-line C program. Here's the 10-line spec for it. It's cool, but I feel like you might be going in the wrong direction. You might be recursing up when you should have been recursing down. So maybe, just maybe, and here's a horrible thought, maybe the entire value of the verification process is ensuring that there is a way of describing the system you've got that is actually simpler than the system. Maybe invariance, maybe all of this, maybe the spec is just, there is a simple, consistent architectural model. Maybe all we're doing in verification is just forcing people to build systems in ways that there are simple and consistently correct ways of describing. If that's the case, then fuck it, we're still winning. That's a major achievement. But yeah, maybe that's actually the value of the verification. Yeah, and here are some horrible, horrible thoughts. There's a lot of things that you're like, oh yeah, it's fine, you just write the spec. What about get opt long? So this is the command that takes your options flags and parses them and sets the right values in a data structure that you passed as a pointer to an array of data structures. This is the concluding exercise, and maybe you want to go at it over lunch, but just to think about which of these systems can you make formal, which of these can you make formal, and which techniques would you use? For which of them is automatic important? Which of them is no misbugs important? Which of them is no false alarms important? So I'm going to put that back up in a minute. Oh yeah, everyone's got a slide where they go the future, and it's all the things that they're interested in, but actually, you lot are the future, right? This is just me being biased. I've got some thoughts, but obviously, like every slide, it's just the stuff I'm working on. So anyway, conclusions. First thing you've got to think about, what's the system? What's the spec? Are they formal? Could they be? If they are, then how fixed are they? Are you verifying written software? Are you writing verified software? What kinds of evidence actually support your goal? You get 2, but only 2, you've got to work for the 3rd. And you fit the process to the tools, or vice versa. That's the real skill part. Anyway, thank you so much for your time and attention. You've been incredibly patient. I've kept you from lunch. I'm sorry about that. Yeah, that's it. I'll leave you on the exercise. Also, can we have a round of applause for our fantastic AV support as well?